Hey everybody, we're doing 1.8 logarithmic functions. So let's just start with an understanding of a logarithm. For some reason it's actually pretty simple, but a lot of people get very confused about it. So let's make it simple. Suppose I told you I had two raised to some power is equal to 8. I want to know what is the power I'm raising. What is the power that I'm raising to 2 to get an answer of 8? Well, think about it. You know that the answer is 3. 2 to the third. And that's it. That's what a logarithm is. This is the same thing as saying that the log of 8 base 2 is equal to 3. So for example, in other words, the log of 8 base 2 means 2 raised to what power will give you 8. So it's the same thing we had over here. So when I write it this way, it's easy because we're used to seeing exponents. When you write it this way, it's a little bit, it seems very cryptic and confusing, but it's really nothing more than this. That's why I'm saying it's logs get a bad rap sometimes, but we're trying to make it log friendly. By the way, if a bunch of mathematicians would start a band, I think they should call themselves the Logarithms. Get it? Logarithms. Anyway, let's do another one. Suppose I said the log of 100 base 10. So 10 raised to what power gives you 100? Well, the answer is 10 raised to the second power. 10 to the raised to the second power equals 100. In other words, 10 to the second power equals 100. So writing that 10 to the second power equals 100 versus writing the log of 100 base 10 is equal to 2, it's really the same thing. Really, it's two ways of saying the same thing. Why do you have to have two different ways of saying the same thing? Because it really depends on the problem we're attacking. See, if we have, if we know the exponent, if we know the base, we know the exponent, then we want to figure out the answer. But sometimes you know the answer and you want to figure out you need to figure out the exponent of how you got to that answer. It's like it's like forensic math. Here's a dead body. How do you in other words, typically in a math problem, we'd say 2 to the third power equals what? And then you would say the answer, 2 to the third power equals 8. But in a log, we're saying 2 to what power equals 8, and then you fill in the third power. So what is the log? I'm going to write a couple of log thingies here, and you guys fill it in. No calculators, just use your brains. The log of let's see, 64 base 4. So 4 raised to what power gives you 64? The log of of here's an interesting one. The log of 2 base 4. That's an interesting one. Okay, so 4 to the third power equals 64. So the answer is 3. Because 4 to the third power equals 64. Now this one is actually 1/2 because 4 to the 1/2 power equals 2. That's pretty cool. So you could have like a fractional kind of log. Um, and let me lay on some properties of logarithms to you. Okay, here's some log laws. First of all, the log of 1 base b equals 0. Now, the reason I wrote base b because it could be any base. The log could be any base. The log of 1 from any base is 0 because b to the 0 because that's because b to the 0 power equals 1 no matter what the base is. The log of b base b is just 1, and that's because b to the first power equals b. Now similarly, the log base b of b to the nth power is equal to n because b to the n equals b to the n. So it sort of follows. Here's a very important one. Well, they're all important. Everything's important. Here's another important one. If I have the log base b of a to the r power. That's equal to r times the log base b of a. And that's a famous thing. Again, if you this is something you've seen in algebra, that when you have the exponent in a log, you can kind of bring it out to the front. That's the way of saying it. It becomes a coefficient. So the log base b of a to the r is r times the log base b of a. These are some of the fabulous rules of logarithms. Now, you remember when we explained when I explained what logs was just a few minutes ago, you saw that this kind of it's kind of like exponents backwards, and there is an inverse relationship between them. In fact, the log well, I actually kind of showed that here. The log of b to the n. So if I take a number b and raise it to the so if I take a number x and I exponentiate it, means I raise it to an exponent of some other power, and then I take the log base b of this same number, I get x. In fact, I actually saw that in rule 3. But I want to also say that if I would do the opposite, if I would take the log base b of x, and I would raise b to that power, that would also equal x. So b to the log b of x and the log b of b to the x, both of these just equal x. In other words, the log and the exponent kind of cancel each other out, and which makes sense because they're inverse functions. Now, I'm going to add a couple of more. Well, when we let's see. When the base equals 10, we just write log of x. We don't bother writing in the base. Normally, you have to write the base so you know what numbers. Like here, you write the base so you know what number is being raised to a power. But since it's very common to use base 10. So if you just write log x without the base, that means base 10. And the base equals e, and remember e was 2.718. So the base equals e, we write ln x, and we write ln x, and this is actually, as we'll see in calculus, this is actually a more natural way of writing it. So this is called the natural logarithms. So the natural log is, we write ln x, and it just means log base e. And and so instead of writing log, so we can't just write log because we're using that for this guy. So write ln, natural log. And this is in a nutshell. Now, I want to show you why we would use why and when we would use logarithms altogether. So let me go find a good, nice example of you. I'm going to go to our Google Doc for a second. All right, I just want to share my screen with you, and here we go. So here's a problem. Let me just put it right there. Okay, so in the last section, we predicted that the population in billions of India, T years after 2008, we predicted that by using the function f of t is equal to 1.14 times 1 plus 0.0134 to the t power. Now, if the population continues following this trend, when will the population reach 2 billion? You see, we asked it differently. We see in the last section, we were just dealing with exponents, exponential functions. So we just said, so we gave you a problem like what is the population going to be 10 years from now? What is it going to be 12 years from now? What is it going to be whatever? So we plug in t equals 10, t equals 12. We plugged in different values of t, and we got answers. But now we're asking kind of from the opposite direction. We're saying, without asking what is it going to be after 10 years, we're saying what year is it going to be at what year will the population be 2 billion? So we're kind of working back. We're giving you the target population, asking you to work backwards to figure out the time, and that's where logs is going to come in. So this is easier for me to work out by hand. So I'm going to switch to the other camera. Let me just we'll be in good shape. Switch. Okay, so we have here, let's just straighten up here. So f of t is equal to 1. F of t, it's making shadows. F of t is equal to 1.14 times 1.0134 to the t power. But we're not giving you a value for t to plug in and crunch it out. We're telling you what the population is going to be 2 billion. So we're telling you that f of t is going to equal 2 billion. So I'm going to just write 2, because that's what f of t is going to equal. That's what whatever many years this is, f of that many years is going to be 2. And that's equal to 1.14 times 1.0134 to the t power. So the first thing I'm going to do is I'm going to divide both sides by 1.14. So I get 2 over 1.14 is equal to 1.0134 to the t power. Now what I'm going to do is I'm going to take the ln of each side. See, that's where it's going to come in to solve. I want to find t, so I'm going to take the ln of each side. So I'm going to take the ln of this side and the ln of that side. Now remember we said that when you have the ln of a number to an exponent, you can bring the exponent out the front as a coefficient. So I get ln of 2 over 1.14 is equal to t times the ln of 1.0134. Now, but the ln of 1.0134, look, it looks very scary and ugly, but it's just a constant, and I could just divide by it. Ln of 1.0134, so that cancels. So t is equal to the ln of 2 over 1.14 divided by the ln of 1.0134. And this looks hideous and ugly, but it's just numbers. It's just a number that you can crunch into your calculator. And you crunch it into your calculator, you should get approximately 42.23 years. So it should take about 42 years to reach 2 billion people. There you go. So again, that's different, and that's why we want logs. That's why logs are important, because if all you have is exponents, I know to crunch in the exponents. But if I have the answer, I want to find out how long it took to get to that answer, what it took to get to that answer. That's why you need logarithms. The last thing that I want to do now is to just show you the graph, the log graph, and specifically I want to show you the relationship that has with the exponential graph. So let's switch over to, let's see, I gotta switch. First, I gotta switch cameras. I gotta go to that camera right there, and then I gotta share my screen. And okay, there we go. So suppose I have y equals, I'm gonna write, let's say ln x. So that's y equals ln x. And it looks a little similar to the exponential curve. In fact, I'm going to draw y equals e to the x. And then I'm going to draw a line, y equals x. There's a reason why I'm doing this. I want to make that a dotted line. Okay, it's a dotted line, and there you go. Done. Now, the reason I made this a dotted line is because there's a certain symmetry here that I want you to understand. The symmetry here is that when, since log and exponents are inverse functions, there's a property of all inverse functions that they're symmetric with respect to the diagonal, that diagonal line, y equals x. That's why I made that a dotted line. So that's not really part of the graph. That's just showing the symmetry point. Now I happen to choose ln and base e. But I could have chosen any base. Suppose I would have chose y equals log. Let's see, how do I do the log? How do you make a subscript of this? Functions. Illustrate functions. Log base b of x, and then over here I'm gonna put y equals b to the x. And right now let's set x equal 2, for example. So I chose x equals 2. So if you notice, let's see, I want to make these disappear for a second. So this is y. So right now b is equal to 2. So this is log base 2 of x, and this is 2 to the x. And if I let b, if I move b, if you notice, it changes. When I move the b, it changes the graph. But they're always going to be symmetric. By the way, b has to always be positive. And of course, there you go. That's beautiful. And that is fabulous. By the way, notice that the domain of the log function is only positive numbers. Notice that x on the log function, x never ventures past it's asymptotic to the y-axis. So it's always a positive number. Not only is it never negative, it never even hits 0. The x that goes into the log, that x right there, is always greater than 0, never less than, and never even equal to 0. That's a big thing about logarithms. Well, now you see what the log graph looks like, and you see how it's kind of the symmetry that it shares with the exponential graph, and that, my friends, is the story. Well, everybody's been fabulous, wonderful. This is actually the last of review video. From this point on, we're actually getting to the real calculus. So that's coming up. Next. I hope you're as excited as I am. Okay, everybody, it's been wonderful. See you guys next time. Bye.